Welcome everyone. Thank you for joining us in this webinar, the whole Lotta stream, where we'll talk about the Streamhouse evolution at Fresha. So, basically, Fresha's journey into all these interesting concepts and what the Streamhouse architecture means in general. Now, today I'm joined with my partner in crime and dear friend, Anton Borisov, who works at Fresha. He's a principal. Um, Architect there. So before a quick introduction for myself, my name is Giannis and I work as a principal streaming architect here at Ververica. I've been working with stream processing for a decade now. And Anton, do you want to also say hi here?
Of course I want. Okay, so hey, I'm Anton. So yes, as Giannis told, I'm working at Fresha where I do some interesting architectural stuff, and yeah, I constantly introduce something new. And I think like this is kind of like a bit of reflexy about kind of like what we built and where we are heading. So it would be kind of like a lot of interesting stuff. So yep.
And for all of you that are watching us, we also have the comments here. So if you have any questions, just write your comments there and we'll address everything. So I don't know, Alan, do you want to share your screen and start telling your story? You have a really interesting story to say. Let's start there with Fresha, what you guys are doing, and then slowly start talking about Fluss and this whole kind of stream house architecture and what it is.
Okay. I guess I'm already sharing the screen, isn't it?
Okay. Yeah.
Okay. Okay, let's go. So today I'm gonna tell you a little bit a story of Fresha on architectural side, and it will be kind of like bigger than usual because I think like I told it in a lot of ways, and it actually covered like real-time analytics, so kind of like some specific problems. Then it was kind of like specifically for about Starbucks. Now it would be kind of like more related to a bigger picture, and I will share like what is the bigger vision. So, but still, I think like I need to get like a little bit of a context where it started, like what problem we tried to solve and how it actually led to the realization that it's kind of like part of a bigger problem that Yanis has something to say as well. Okay, let's go. The problem was super simple. So we had analytical dashboards and widgets, and these analytical dashboards and widgets, they had two ways to load the data. First way was basically from Postgres. You just get all your data, and if it's kind of like in a single database, or you can do an RPC calls to do some enrichments, then it was powered by Postgres. You can imagine that for kind of like big partners. I need to say that Fresha is basically like a marketplace for healthcare and beauty and wellness. And it means that we have kind of like our partners that are kind of like wanting to provide some services for the customers. So it means that these kind of like partners, they can be of a different size. Their customers base is very different as well. So it needs like a different treatment as well. So for small partners, it works pretty fine. You just get the data into your Postgres, do a couple of joins, and everything works. For the bigger ones, it's actually a bigger problem, and we had like a previous solution. It included like some DBT transformations and batching with Snowflake. It kind of like worked, but if your dashboards and widgets are loading for updating every only a schedule every 20 minutes, so you have a problem because everybody would lose kind of like patience, and it would be confusing kind of like UX. So in the end, we just sort everything from Postgres, and that's a problem. So yes, as I said, like we needed seconds to minute freshness to product UX. Most probably we want to balance costs because real-time analytics can be expensive. So you want to kind of like have a control at this. And yeah, you need some tools to be boring for engineers. So still kind of like SQL and kind of like some serving layer that would be nice to have. And as I said, like for bigger partners, we want to have a predictable tail latency because sometimes you get like more or less fine latency until you go to P99. And here is a problem because if you're kind of like a bookings solution, a marketplace for beauty and wellness, then it means kind of like your biggest partners are actually included in your in this tail latency, and they are the most kind of like profitable for you. So that's kind of like a business setup to understand the problem. This is how it basically looks. So you see all these fancy, nice widgets and whatever like, and then you can see that this stuff is actually updated every 20 minutes, and we even have like some note denoting this. Uh, More kind of like nice pictures. So there you can see like widgets. They're pretty kind of like nice UX. About scale. So basically, at the time when I prepared this slide, we had around like 60, 100K bookings a day. So it's around like billions of CDC events ingested daily because, yeah, the main entity is still bookings, and then you need to enrich and do. So if you have like 60K bookings per day, you can imagine how kind of like how many different workloads related to this can be attributed to this stuff. And around like 3K requests per second, I guess overall. Since then, like the load, I think like increased. So right now we are handling, I think like more than 1 million bookings a day, and CDC is even more. It's presented like a bigger problem, but we'll talk about it. Then the goal is super simple. Yeah, it's one problem to define the goal, and then another kind of like to make it work. But here it's a 1 minute of data staleness. So if you want to kind of like serve any sensible analytics to our kind of like customers, so we want that the data should be stale like up to 1 minute. The less, the better. But yes, and sub-second response time. Once again, so this is kind of like a much nicer representation. So you can see the only kind of like part that is added that is new is these 2030 joins and subqueries are very common because as I said, I already mentioned that DBT models that we were running on schedule, they were pretty sophisticated and they prioritized layering. And this layering and different kind of like it resulted that yeah, you need to use a lot of subqueries, a lot of modeling, like joins and whatever. Like so, we have this, and around 100 databases as sources. And yeah, so here you can see like a usual latency. Then you had like some errors, and these errors is basically timeouts. So it's kind of like, for example, 200 errors. It means that someone didn't get this kind of like widgets working. And yeah, it's kind of like the biggest partners. Then what we got in the end? In the end, we kind of like gradually evolved what we wish to do. And though it started like first as real-time analytics problem, so the first kind of like poke into this problem, it was kind of like, okay, let's just try to use like ClickHouse as a usual analytical solution. So I know ClickHouse, so it's kind of like pairs nicely if you can with Flink because you can do all the enrichments, prepare the joins, kind of like once it's in ClickHouse, if you do this materialized view stuff in ClickHouse, then it's blazingly fast. I mean, like maybe you know the story, but what we got, like we got like a sources plane, so it's like the same Postgres database and Kafka Connect plane to CDC the data with division to our compute plane, where our compute plane consists of Flink, of course, and Spark. Then you can do all the transformations and enrichments that you can imagine if you need them with just these two tools. And then there is like a layer of canonical data because we had this problem, and I think like it's very important, though often underlooked. So you get your data with some connector from Kafka Connect into the warehouse of your choice. It's all working until something kind of like happens, and then you need to kind of like consolidate your data back and make it consistent once again. So the usual thing that you usually do is you just go to and trigger the Debezium snapshot. Okay, so you can use additional conditions and other stuff, but still on your operational database, it's kind of like a little bit of a burden to run and monitor and whatever. So I specifically thought about like, no, we need to move to something better. So we need to have like a canonical data representation that would serve as a basis for all downstream processing and usage of the data. So this is like a lake plane where we have like Payman and Iceberg supported. And then we have a sync lane where it's basically like a serving layer that builds on top of the data that is being kind of like processed and ingested through compute plane. With optionally go to canonical data representation to serve like data with different kind of like guarantees. And by guarantees, I mean like freshness and cost of the data, because I mean like data in Iceberg, it's not as expensive as the data in your Starox, for example, cluster. So in Syncs lane, we decided to go, like as I said, like with an ability to plug and play different things, starting from Postgres, Iceberg, Snowflake, Starox, Elasticsearch, so all everything. And the idea was kind of like, okay, if I need to add something, I only need to change like sync, use it in a different maybe connector from Flink or develop, and then optionally go to historical lane to do some historical backfills or whatever like. But this thing that with kind of like historical backfills and streaming data, it's kind of like a two different lanes. So it works. It's some kind of like a Lambda architecture. So can we kind of like unify it with some common tool? And it turned out that we can, because it was like a new innovative database kind of like was emerging in the market, like Starox. And here Starox is actually a unification serving layer, bridging the gap between our lake plane and real-time analytics that is being like ingested into Starox. So all good. It worked. So what we achieved regarding to this. We achieved kind of like a clear separation with how I call it is lanes of data. So first lane of data is an ingestion spine. So it actually kind of like stays this almost the same since the time when we decided to introduce this new architecture. So you just kind of like CDC in data into Kafka, and once the data in Kafka, like your common message bus, you go and get this data with optional transformations and kind of like convert to historical canonical representation with Iceberg or Pymon, and then you can use federation. So basically, you write a SQL query and you can reference like a catalog. And catalog is a notion of external data source. So if you have like an Iceberg data living somewhere, I can reference it in my SQL query in Starox. So for kind of like a developer trying to use Starox is just kind of like a matter of specifying a join with an external source. So it's kind of like a unification layer. It works, but you still kind of like need to do it like manually, and you still need to understand like separation between like cold data that is or cold canonical data that is living like in a lake, and real-time data that is kind of like native to Starox. So yes, it's kind of like where we would dig a little bit more. And then real-time lane is just like Flink ingestions through Flink connector to Starox internal, and then you execute SQL queries, and the rest is kind of like, and I also presented like a text search lane, because it's also kind of like a story about like federation and common data representation. Because imagine that Starox like capabilities of Starox, you don't like full text search and other stuff. You want like some advanced rankings, and you know the tool to do it. It's basically Elasticsearch. So what it takes for you to use Elasticsearch, because usually the data how an application is handled, like when you don't have the ability to have like a canonical representation of the data and federation, it means that you just kind of like go specifically kind of like configure access to Elasticsearch, you query Elasticsearch, you get some IDs returned, then you use these IDs to additionally filter the data and return the result. So it works, but there is a lot of tedious like work behind this, so it's not ideal. So like once again, this architecture it relies on federation in Starox as a union layer, and it works. Then let's define another characteristics, freshness tiers. So once you have like data, it actually makes a lot of sense to assign some tag on the data. And this tag is the data can be hot. So I want this data to be as fast as possible with the least staleness in terms of freshness, and I want to see it like immediately. So here you just kind of like forced to use Kafka, Flink, and other kind of like tools that are kind of like suitable for real-time processing. So stream processing engine and some uh, serving layer that can be powerful enough to get the data in a way that you want. So in our case, it's Starbucks because you can just express with SQL, and then with the help of a sophisticated engine, it just works. Then warm data is basically mostly it's a territory of Pymon. So you just need some kind of like cheaper store, and the data should be kind of like materialized there with some kind of like uh, a little bit lower freshness, but it should be more dynamical in order to support like the notions that the data can change and you need to quickly integrate these changes with some predictable schedule. So as I said, like warm data is kind of like we are talking about minutes. And then there is a story of deep history data. I'd like to think about it. It's kind of like mostly immutable. Of course, reality is kind of like is not that forgiving, and in this kind of like regard, you wouldn't have like a strict immutability. But I'd like to think about it is kind of like okay, you define like an operational range of time range of the data that you support. So let's say that my application or my architecture is mostly interested like for the previous year and this year. So I just defined that it's kind of like a boundary for hot data and warm data. And then deep history is something that is kind of like out of this time range. How do I wish to have? So I may relax some guarantees. I may say like, okay, if your data is so kind of like old and somehow I have updates to this data, these updates would be integrated like daily. And sometimes it's a good trade-off because sometimes it just your customers wants to access your data for some investigations, for some reports that are kind of like historical one because and it doesn't need to be kind of like super kind of like fresh or integrate all the recent changes, or it can be kind of like be integrated with recent changes on demand. But what do you get like with this immutability guarantee, like deep history data? So theoretically, let's suppose you kind of like process this data, you decide it and know exactly the layout that you wish to support. Because, for example, you want to provide some kind of like user interactions like 5 years ago. So, and you say like, okay, I kind of like spent some time, I modeled this data, I defined like the data layout that works for me, and then with the help of some engine. I'm mostly talking about Iceberg, by the way, here. And Iceberg is pretty efficient in reading. Not pretty efficient with freshness guaranteed, but with reading, it's kind of like pretty sophisticated. You just get this data, and this kind of like getting this data is easy, fast, and cheap. So for kind of like data for 5 years ago, I wanted to make to be queryable, but I want to pay the least amount of money for it. It kind of like makes sense. It's easy. So this kind of like data tiers, I think like it's a nice and easy concept to understand. So let's go. As a result, when we kind of like introduce this new architecture, and by the way, we were the first in UK to actually try Starbucks and make it to production. What we achieved. So right now, the result is kind of like from 12 seconds of P99.9. So for our biggest partners fall into this category, we reduce it to 300 milliseconds. And yes, as I said, like 1 minute freshness. Yeah, well, you can achieve it totally with Flink and Starbucks, what I'm talking about. No more timeouts. There is a spike of some errors, and as you can notice at the bottom slide, but it's kind of like our experiments with deployments. So trust me, it's not something that we kind of like missed. This architecture is good. This is another view of results. So as you see, like I defined like that we achieved the result for P99.9 of 300 milliseconds. But basically, if you take a look at other kind of like tail latencies, they're actually pretty decent and ranging from kind of like 13 milliseconds to 80 milliseconds most of the time. And there are different like dimensions of the data. So kind of like sometimes you want to get invoice by date. Sometimes you want to kind of like get invoice not only by date but some additional filters. So I decided to cut the captions here, so, and you see kind of like some duplicated captions, but it's just like a different facets of the same query needing a little bit different filtering and processing. This is kind of like another interesting results that we achieve with this architecture, and I like this slide particularly because it's one of the guys from our team that was integrating all of this. He tried to compare the solution based on Postgres and on Starox, and it's not very fair, but it's even more impressive because uh, kind of like take a look. So for the data to get for 30 days with the old architecture, it kind of like was not loading for 1 minute. With new architecture, it kind of like it was able to return the data for the whole time range under 4 seconds. So of course we iterated, we optimized like, and because like as I said, like our reports and dashboards, they require a lot of joins. Sometimes it's as easy to just kind of like let our kind of like OLAP engine to do all the job and kind of like figure out like um, the optimal order of doing joins. But when it doesn't work, because I mean, like you need to go a little shift a little bit left, and shift a bit left is kind of like in terms of our architecture is go to compute layer, and we do some join transformations in Flink with this, and then we kind of like pour this pre-join data back into our lab Starbucks, and it just works. So we did a couple of join optimizations, and it resulted like more or less stable tail latency. Then average latency is under 1 second. And yeah, it's kind of like a complicated use case. So this is a little bit another use case. I'm just kind of like demonstrating that this architecture is capable to adapting to different kind of like data modeling requirements. So right now we have, to summarize, right now we have a pattern how we work with real-time analytical data. So usually we just get the data through ingestion spine. We get this data into kind of like our canonical format first, like iceberg pymon. Oh, this is my cat, I guess. Sorry. And then once we get this data into historical layer, okay. And then there is a time for real-time lane. So if you first, when we kind of like model a new feature, we just get all this data into all up like Starbucks and let it do its work. If we are happy with the results, then we stop. It's good enough. So if kind of like we need to get the data for all the period, we just go to our lake and federate with Starox. And then if we are not happy with this, we just go to compute lane and see what we can optimize, what is the problem, can we kind of like relax some requirements. And this means that we kind of like employ a lot of Flink transformations. And it's kind of like right now it's an iterative process. It's not like that we need to kind of like lift the whole modeling and kind of like optimizations pipeline before actually achieving like some baseline results. That's the big achievement. Uh, if I kind of like take a step back even more, and let's see what worked in this architecture. Because what worked and make it cheap, by the way, because I mean, like we are kind of like a product company, so we should care about like the guarantees, SLAs, and also about costs. So if we kind of like use a canonical representation in data lake, then it's cheap. If we do zero or minimum duplication, then it's also cheaper. If we kind of like can unify compute and kind of like federate, it's a little bit related to the previous one, but in this kind of like sense, it's also kind of like about can we provide a unified interface to do with the data what you want, or you need to kind of like do some gluing layer with an additional set of tools and try to mix and match different data representations against them. So in this sense, kind of like this architecture is pretty okay if it goes to real-time analytics. So once it's kind of like out of federation layer of real-time analytics, it's kind of like you still need to understand like what is your data representation in Iceberg, what is your data representation in kind of like Starbucks internal? Do we need to do an additional transformations and get this data somewhere else? So it's not ideal, but still kind of like this for real-time analytics, it works. So and then union read. So by union read, I specifically named it, but it's basically like a old good federation layer. So when you kind of like make your query, ideally, you don't wish to think about like where this data comes from. You express your guarantees and kind of like expectations from the data at the modeling stage, where you say like, okay, this data should be kind of like cheap. So I want to make it, I want to make this trade-off visible. So I say like, okay, if you query the data kind of like 5 years ago, then it would be cheap, but the data might be not very up to date. All this data is kind of like super fresh, but I pay the most for this, so I need to kind of like build a lot more monitoring and other kind of like additional kind of additional concerns related to this. So this is kind of like boils down to the question, and the question is super simple. So we solved this use case, and we got like more or less coherent format architecture involving the set of tools that we decided to use. So all up engine that is capable of federation. So we built a caching layer to kind of like optimize the cost and capabilities. Then we have a lake format as our canonical representation in a different kind of like format, but still very easy to federate with some set of rules as a Starbucks internal format. The question is, can we get like a more generic solution and kind of like solve it not only for real-time analytics, but as a generic solution? And this is a question that kind of like arises because as I shared like on the previous slide, so this is surprisingly looks like a bit like the set of problems that is the promise for Streamhouse architecture. So we want some uh, uh, data representation that would allow us to seamlessly integrate like real-time guarantees and historical guarantees and hide it behind like some common interface, but very kind of like flexible and hidden for the end user. So yes, in our solution, it's actually kind of like still possible. We need kind of like some streaming storage engine that would hide the pain with working with different kind of like data representation and different guarantees from this data, but providing a unified interface not only for analytics but for the whole stack. And once we have this tool, and you know the name of this tool already because I have a slide, it's Fluss. Apache incubating, you can rely on a different, you can actually use a different mindset and you can build more sophisticated solution with it. Because first, how we actually heard about Fluss and what we thought like would be like a killer feature for us initially. I mean, like then our perspective had shifted a lot. It was kind of like, okay, we have Flink jobs and we have like a big booking stable. And this big booking stable is needed almost in every kind of like pipeline. But because of some modeling kind of like considerations in the past, this booking stable has unbounded state, for example. So we cannot say like, oh, this booking is actually kind of like happened 5 years ago. So it's kind of like we have a guarantee that this booking wouldn't be modified in the next couple of hours or we don't care about. No, we want like a consistent view and recurrent bookings are also expressed with this kind of like database table. So it's more complicated than this. So our main pain with the current architecture is that we need to replicate this bookings table state in every single pipeline that we have. I mean, like, since kind of like getting this architecture, we are running Flink 2 with disaggregated state. So it's kind of like a little bit easier. though not ideal because, for example, Starock's Flink connector is still not supporting Flink 2, and I kind of like asked about it, and I think like I might help with it. I almost have a working solution for this. At least it's kind of like in POC, so we need to test it. But once we have it, we would be very good. Because right now we kind of like have a cluster running Flink 1.20 and Flink another cluster with Flink 2. And kind of like the only thing that is holding us to migrate fully to Flink 2 is just kind of like that we need to do ingestion into Starox, and we use Flink connector. Flink connector is only kind of like for Flink 120. So back to the main topic. So we have Flink jobs. We want to reduce the state footprint for this because it's kind of like hard to monitor the state and it's kind of like getting a lot of duplication. So first, when I heard about like Fluss, I said like, okay, but it's kind of like an ideal. So we can get this kind of like state, have more or less the same real-time guarantees that we want with Fluss because it's kind of like streaming storage that supports like real-time updates with like good guarantees. And then we can say that Fluss would become a canonical representation of the data that was before internal to Flink, to a single Flink job. So it's a big deal because once you have like a canonical representation of your data used as a Flink state, I think like it's easier to manage, it's easier to monitor, it's easier to kind of like treat in your architectures. Then another big deal for us, it was kind of like a delta join because I mean, like you all know the story with Flink joins. There are different kind of Flink joins, and sometimes and they all have their different trade-offs. And kind of like I think like for a lot of use cases in at Fresha, we're actually pretty okay to use delta join eventually. I mean, like we tried different approaches how to actually make joining the data in Flink more approachable by, for example, our engineers, because our data engineering team is not that big, and we specifically want to avoid like operational complexities related to the tooling that we use. And kind of like Flink is one of our main tools, and but Flink is sophisticated, and if you're kind of like not into this, so it's very hard to just tell you, okay, oh, you need your data, for example, in your Starox. Oh, it's actually kind of like you tried it and it didn't work when you just joined the data. So in order to do it, you need to just go and write Flink job. It would be ideal if it would be like so, but then there it would be kind of like, oh, I'm not Java developer. Oh, it's very confusing. I don't understand. So you can provide some additional tooling. You can create an additional abstractions that work for your organization that reduces this mental burden. But at the same time, kind of like sometimes you just kind of like want an easier solution. And in this sense, I think like Flink Fluss might be a big deal because the idea is basically I want to have a stream to stream join with the same guarantees as a stream to stream join, but my bookings data, for example, it doesn't change that often for the period of like I don't know, like next 2 3 months. So I want to only pay the biggest amount of money and maintenance cost for this data. The rest of the data, I'm pretty okay if it would be kind of like looked up, and Delta join provides this guarantee because in a sense you just have the same stream to stream join. You have some caches that you can say like this data would be returned super quickly once something happens on any side of the stream. And then you if something is not found in the cache, you just go and look up into your streaming storage, the actual Fluss table, and then the data would be returned. Of course, there are a lot of limitations, and I kind of like, because I'm very invested into this topic, I contributed a couple of articles where I kind of like looked at the delta join feature, and I kind of like studied all the shortcomings and limitations and set of trade-offs and when to use it and when not. But it might be good for your workload if you are working with unbounded CDC data and you don't wish to pay the tax of state as much, but you want to have it under some control. Like big strong limitation right now, it doesn't support like deletions, and I don't think it would happen in the nearest future like this support because it would require a pretty sophisticated like retraction mechanism. So what you wish to do, you may convert like your deletion to soft deletions and still be able to enjoy like delta join. So take a look. I think like it's cool. Okay. So what else? So we got like let's take a even bigger look what we can achieve with Fluss, for example. So imagine that you have like a historical data in your iceberg lens or Python format, and it's cheap and it's kind of like easy to operate, or at least you know how to operate with this. And then you have like a real-time lane uh, with Fluss in key value tables. And then you want to build, like, for example, a feature store for your ML pipelines. With Fluss, it's kind of like natural because the biggest like problem with all of this is that you need to support like the same data representation or at least the same pipeline that you used for training, and then you need to use the same for inference. So in this sense, like you would have like a Flink as your compute engine that actually does all the joins and other transformation. You have a canonical representation of your data in Fluss, and then Fluss as a streaming storage engine hides all the tiering and representation of the data with union read. I think like it's kind of like a very promising architecture, and I bet we will see the application of Fluss here a lot in the nearest future. So full picture. Full picture, yes, compute layer is Flink, unified storage is Fluss and lake tables. And serving layer, you can literally connect anything that you want if it supports like Fluss connectors. So I think like the story of Fluss would evolve a lot once the adoption would be a lot more, when community would provide more connectors, when a lot more tools would be interested to integrating with Fluss, then it will be kind of like a rise of this new architecture building on top of the streaming storage that hides all these complexities. So right now you can use Flink. You can build some retrieval service that employs like some client. I know that Fluss has. Well, I not I know. I also contribute. So there is like a Fluss client bindings for other languages. Like right now, it's Rust, Python, and C++. So it's under active development. So I can imagine that once it would be kind of like released and support all the basic operations of Fluss, you can just kind of like say, oh, you want to use the data from Fluss. So you just create, if you have a binding to your language, you can retrieve the data and do whatever set of transformations that you want. And kind of like, it's a big deal, I think. Like, but yeah, I know that Spark connector is also under an active development. I'm also thinking about like, for example, what if Starox supported like this connector for Fluss? So, for example, if right now I need to specifically kind of like write SQL and watch out for kind of like these cutoff points to say like, okay, this or do an additional modeling step in my models to say like, okay, this is actually the data that is real time, and this is the data that should be tiered, and I want to pay him like with this data more. And I'm okay if I'm 90% of the time querying like real-time data, so the latency would be super quick. But if someone wants to kind of like get a mixture of this data, so the tail that actually resides in a lake, it would kind of like take longer time than to get real-time data, and it would dominate the latency of your request. But if it's all hidden in some unified storage layer, like Fluss, well, it's a lot easier to reason and it's a lot easier to actually write the queries because all this kind of like tiering and data representation, it can theoretically be expressed like by Fluss. And now this architecture is actually kind of like starts to make more sense. And as I said, like before, we treated like Fluss as a replacement for as a tool to externalize Flink state. But right now, it can be like an external state, not only for Flink, but for anything that is kind of like willing to work. And then all this externalization and kind of like tiering is hidden. This is a big deal. And I think yeah, Giannis, do you want to add something here? Because I think like we reached your slides. And
Oh, it's we talk as well. Man, this was an amazing presentation. And a few things I want to share here is that first of all, I will never forget it. I met Anton, like, I think it was around September, and he came in the Flux community. He was like, I will never forget this phrase. He's like, I saw Flux like 6 months ago. It seemed great. I'm like, I'm going to say it in 1.5 to 2 years. And then he joins like, dude, it progressed so far. And this is to highlight that basically there is lots of work going on in Flux. And also there are many people like Anton now, like extremely smart people that go and contribute things like the Delta joins. He picked up all the things around the Delta joins. He contributes a lot on Flux, the Rust SDK. So there's lots of work taking place there, and as they said, they also invest a lot into Starox, which is an amazing piece of tech. And I think I have heard so much Starox over the last year; it's crazy. And to the best of my knowledge, you're also one of the first that start deploying Flux there in the UK. So lots of
yes,
stuff.
there would be a lot of interesting to come because, as I said, like architecturally, we see the need of Flux, and right now we are in an active process of actually deploying our Flux. And first, we enjoy like this Flink state reduction. Then it would be kind of like a time for delta join and modeling. But theoretically, in the end, it would be kind of like okay, we would contribute, I think, like to a lot of development around Flux, kind of like take part in the connector development, and yeah, it's just kind of like evolution, as I said. Thank you.
Oh, do you want me to share my screen now, just so you don't have to work with the slides?
Ah, okay, yeah, sure.
Let me.
Sorry.
Okay, now. Uh, so basically, I uncovered lots of things. So I have this thing, and I want to go back into primitives and architecture as I always do. So he talked about the compute storage separation thing. He talked about flows and feature stores, and so many other things. Now, I want us to take a step back now to just see the way we have been doing things all this time and what we try to do now with Flux and this kind of Streamhouse architecture. And basically, the status quo these days and we have been doing for a long time in terms of streaming architectures, basically similar to this. And I'm pretty sure that everyone here has seen these things. And this is what I call Kappa or modern Lambda architecture. And the way I put Lambda there is deliberate because Kappa architecture by nature doesn't have, let's say, any batch process or historical context involved. So these days, when we try to use, let's say, open table formats, we again split these two layers, we split these two worlds with completely different semantics, and we'll see here what this means in practice. So it's basically like recreating a modern lambda architecture. So on the streaming layer, we always have the data ingestion there and goes into a topic-based streaming storage, which is something like Kafka. And we need to maintain an XML schema registry, right, to reason with schemas because everything is byte oriented and there's no reasoning in terms of schemas. Now, we typically have this data, we decentralized it, like we have our different databases, and all of database we want to query the data. If we do want to do like stream processing like with Flink, we need to copy the data on Flink state again and have heavy states. These days we also have vector databases. And on the other hand, if we want to offload the data, basically we have the data lakehouse and we use open table formats like Iceberg, Pymon, Delta, or Hoodie. And this is where the separation of the two worlds starts again. And then when we operate on the data lakehouse, we have this let's say logical representations, these logical layers that we create in terms of bronze, silver, and gold tables, which basically have to do with the data quality that this provides. And we typically schedule this, creating these jobs on daily or hourly intervals. The problem with these things now is we decentralized everything. We spread out the data of a different place. And if you think about it, right, we have the data on Kafka, we copy the data on vector databases, we copy the data on key value stores to look up the data. We copy the data again on Flink state. We copy the data on all of databases. We copy the data uh, on object storage. And basically, with this data communication, we have data hubs, we have lots of network traffic going on. We have here, when to schedule jobs, I have workflow schedulers. And if you think about at the end of the day, if we do things like, Kafka topic and consume with Flink right back to Kafka, these Kafka topics actually have zero business value. They're just intermediate pipes through which we move data. And if you notice every single one of the systems here, it's all about they have the same single abstraction. And this abstraction is a table. This topic-based streaming storage is the only thing that doesn't have this abstraction, and this is how we have been modeling the streaming space for years. So basically, this doesn't allow us, let's say, the way I like to put it, in terms of extracting a common denominator for all these things. And this is what we changed with Fluss. We treat streams as tables, and this at this point we have a common denominator for everything in terms of the table. So what does this mean? So let's take a step back. Think of the lake house as a foundation, right? Let's take iceberg tables as an example. And it's open shared storage, which means it's storage that is reusable for every engine, right? Because it's a form of computer storage separation. You have the bronze, silver, and gold layers. So if we follow this meta model, we can realize that by adding on the hot layer also this kind of tables, we basically have the historical data, which is long-term minute or hour latency or even more, and the real-time layer, which is the short-term in terms of seconds of milliseconds of latency. Now, by building on that, like we have bronze layers, silver layers, gold layers, and this opens a new metal model and a single table abstraction where basically we have what I like to call one table and one SQL. So a single table abstraction, and you basically have different freshness layers. You have the hot layer, you have the cold layer, and you run the same query, and it doesn't matter whether it's historical or real-time data, the edging and the storage layer itself is able to understand the data it needs. So basically, this is the result, and this kind of, let's say, Streamhouse architecture. And the other part is what it reasons about is data continuity. Like before, we have to do things and have workflow schedulers, all these kind of things. Here, it's basically similar to the CAP architecture. It's all about data continuity and everything being a stream and treating them as continuous flows. And even on the code layer now, we have incremental updates and tables that get continuously updated. And basically, we have everything is a stream, but we have direct access also to the historical data whenever we need it. And for me and the people we are working with, it's also this is how we see what we see as the future of modern streaming data architectures and what we need to truly create intelligent systems. Because if you think about it, right, how many times you have heard like the modern AI era, for example, requires streaming data. But what we do there, and if I go back to this approach, is basically we spread out the data and we feed every single system with fresh data, only to aggregate all the data back again for context engineering, whatever we need to do. So with this approach, everything is already centralized. You can think of it as a decentralized versus a centralized, let's say, approach. And this is the end result. We have the Apache Fluss cluster, which can store uh, it has basically the primary key tables and the log tables. The log table act exactly as a message queue in Kafka, but with columnar streaming and database like properties. We have the primary key table, which consists of the key value store and the log store. And basically, every table has the ability, it's a centralized place uh, where you can ingest any types of data, including multimodal data like audio, text, images, and everything. It has row-oriented data store, it has a columnar data store, and it also supports vector embeddings and vector data. So it's a single centralized place for all your kinds of data using a single table abstraction and a zero copy tiering between the hot layer and the lakehouse tiering. And finally, because now we have the streams as queryable tables, we can apply all the different techniques we are familiar with from the database world to achieve querying only the data we need in every case. So, for example, if you want to do column pruning to avoid transmitting lots of unused columns, or you want, for example, to run predicate pushdowns or partition pushdowns, now all these things are feasible. Basically, we create a queryable, let's say, streaming database kind of thing. So this is also what I had on my side. I think we covered lots of things there, lots of interesting stuff from Fresha. Uh, this is what I have to say on my part. So I don't know if there are any questions now. I think we are we have 10 more minutes for questions. If there is anything, let me check. Actually, Anton, I will start with you if you have any questions. But what questions? You know these things already, right?
Yeah, kind of.
Let me try and see. I see one question from David, but I missed the context because the only thing I see, probably there is something more which I can't see.
Ah, okay.
I mean the
Well, the
data.
question was super simple. Which tool did you use to visualize your data? So
There,
from my side, it was Excalibur. So I just used Excalibur because I don't know, like it was the first tool that I used to visualize the data. So I'm just getting better in this. And it has this kind of like vibe, nice vibe of kind of like hand drawing. So I just like this tool. Don't know what do you use, Giannis, by the way.
there's another one that says the dashboards where you said they are updated in 4 seconds now,
Hmm.
which is there is probably a question somewhere before that, but I can't see it for some reason.
Hmm. I mean,
So
the dashboards where you said they are updated in 4 seconds now. Okay,
there is
let me
another
check it.
question from Vijaya. We need to compare how easier this is when compared with Databricks kind of system in terms of usage and experience. Um, I think I will need a bit more context here in the sense that we're discussing about completely different systems and completely different worlds. And Databricks basically it's about basically there's differentiation between, let's say, streaming and batch, right? And the way I like to present it these days about streaming is more about the, let's say, machine decisions, and batch is more about the human decisions. Basically, Databricks is more on the bad side, and for generating, let's say, human decisions. But in terms of user experience, I'm not sure what this means. We're comparing open source technology and architecture with products, so I don't know if you have something to add to that, Anton, some thoughts on that, because I also know you're
Uh,
Snowflake a lot.
yeah, I think like, in my opinion, I mean, like I absolutely love open source because it gives me an ability. Because if you want to be innovative and experiment with bleeding edge technologies, you cannot afford to don't know the implementation. You cannot afford to not to kind of like dive into the technologies, the code, and kind of like make sense of it. Because I mean, like, imagine this. So you kind of like invested in some kind of like maybe known for others technology, and then you have a problem, and then the only thing that you can rely on some customer support like forums and whatever. I feel if I want to move at my own pace, I want to understand the tool, and I'm in this kind of like sense, I'm a big fan of understanding the tool and technology and not getting it blocked. So in this sense, like Databricks kind of like stack for me is not ideal, and I can only assess it from the side that if something goes wrong and I want to fix it by myself, I wouldn't be able. And for me, it's a big limitation.
So the other question now is how would we implement this in AWS? I mean, what are the challenges? Uh, and I think you're also, guys, Anton, you're deploying on AWS, right?
Yes.
So on top of my
Uh,
head, the only challenges I would think about is in terms of building the, let's say, internal experience if you go and self-deploy Fluss, in terms of how to operate it, right? I can't think of any other challenges out of the box. But since you're down that road already? Have you guys experienced any other challenges so far?
Okay, so it's basically kind of like yes, we decided to go with deploying our Flux cluster on Keras. So the first limitation was basically there were no Helm charts provided. So I remember
No.
like well, the first Flux
Wait.
community call when I kind of like asked, well, can we do something with it? Because it's kind of like a big strong no from our DevOps and SREs. So literally you can create your these Helm charts and other kind of like stuff and make it deploy. But in order to kind of like, because it's like a cross-cutting concern, so it's about like observability, then it's kind of like you need to handle operations, then about data and everything. So, and the best part of it, that basically Flux community was very kind of like helpful in this regard. And David delivered like Helm chart, and now we use this Helm chart, and we were able to deploy our Flux cluster on AWS on Katies, and we continue iterating and assessing what else do we need to add to make it work. And yeah, it's currently ongoing process, and that's kind of like boils down to the previous kind of like answer. What is kind of like the benefit? The benefit is that basically this tool is open sourced, so I went with the community. I kind of like met the right people, and I make it happen because I just need it, and people are interested to help. That's the best part.
Yeah, that's one part I'm really proud of our community, and this is how we also get more cool people involved. Like we have Anton now here, and we are really lucky about that. So the next question now is comes from David, and he asks basically goes back to the other question. Like, I'm not talking about. He deleted it.
Okay, sorry. Yeah, I
Yeah,
just answered. So it was like just Datadog. So we kind of like have we pay a lot for Datadog, which might be not the best thing to do, but yes, we visualize everything with Datadog. So I can reason about this basically by looking at the latency of kind of like our reporting service that we used in homepage analytics like 5 months ago, and how was kind of like the latencies. And then since we kind of like changed to use Starox. Yep, that's it.
So
That's
the next
simple.
question now is from Evangelos. Do you use vanilla Flux configuration? Any tip for fine-tuning Flux Pymon? So in
For now,
my
it's vanilla.
yeah,
Yes.
in my experience so far from the class from the workloads I'm running, the only configurations I might have needed to tune sometimes is basically about the recovery configurations in terms of offloading key value store snapshots and these kind of things. Now, when it comes to Pymon specifically, it depends on what you try to achieve with Pymon. The main thing for me is not Pymon specifically, but rather than how you tune the tiering service resources, basically based on the size of the Pymon tables that you have. So for Pymon specifically, if you care, I mean, if you try out things like union reads, for example, some things I would test is if I want to enable and see the differences in terms of performance with deletion vectors and without. This is the first thing. And the second thing is because Pymon also does automatic compaction, will be around. They added this new cool feature when it comes to the compaction. When it comes to compaction, which is called incremental clustering, and it's really interesting in terms of it selects different layers on the LSM tree that knows how to compact. So for real-time streaming workloads, this might have a really good impact on your performance and the union reads in general. Um, but yeah, but I think the main tricky part here is the sizing of the resource of the tiering service. Moving forward, we might want to think about the service to do more automatic, let's say, resource tuning of the service. But for now, it's pretty much on the user to do some trial and error. The old cool
I mean,
class.
like, there are interesting kind of like considerations. So, like, I
Yeah.
recently was kind of like preparing like priority queue optimization for kind of like downloading remote logs. So
Yeah.
as you say, like Fluss, it has like internal tiering and then external tiering, and kind of like when you don't find like logs locally, you need to go and download them. So the problem that Rust SDK, it just kind of like try to download at the maximal speed. And kind of like when I started like Java implementation in Java client, so it had like a priority queue that actually prioritized downloading the data, the logs for the buckets that come earlier. But the thing is, two configuration parameters, and I didn't know about this before I started to implement it in Rust. And it basically controls how much permits are allowed to start like downloading and how much kind of like permits are available to actually consume these downloaded log segments. And I bet that by fine-tuning these parameters, if for some specific workloads, it would be very beneficial. Right now, we are just kind of like trying to make it work like basic Fluss. So we are not super specifically like deep. We are not in this part when we care a lot about tiering to iceberg or Pymon. We just want to make it work and get it like work as a replacement for Flink state, for example, for our biggest tables. Then it would be a second step is kind of like tiering. We are not there yet, but once we be, then I think like I also kind of like dig more into this, and I have my own opinion that I will most probably kind of like express in some kind of like articles as usual.
Exactly. Yeah, and basically this is also what we observed so far. So the main use case and the way it started with Fluss is basically to do the compute storage separation, let's say, kind of thing, and basically optimize all the things and the problems that Flink users have. This was the first, let's say, wave. Then we saw lots of interest in terms of using Fluss as a feature and context store. So these days also the use cases are all around that. And the third one is that for me, for those that start right now, this is why I also go on the architecture part, because for those interested to create data platforms I start today, because the reality is that business has lots of tools, so it's hard to go from day one from the architecture and Streamhouse perspective. But for those who start now, for example, they might want to evaluate and go that down the direction directly. We'll see. We have lots of work to do, but it's fun work, so we'll see where all these things are heading. So we are on the top of the hour. Um, I hope you guys enjoyed and had fun. Man, as always, it was amazing having you here. Thank you so much for joining us. And yeah, I mean, for those that are interested and want to find out more, please join our Flu Slack channel and we can discuss more offline there. See you all, and yeah, bye.
Thank you. It was fun. Thank you for the invitation, Yanis.